right, chatters. We are going to be on stream today. Okay. Yeah. We're gonna be doing some stat streams today. I'm just gonna double check to see if the audio's good real quick. Gong gong gong. Give me a sec real quick. Okay, yeah. It sounds pretty decent. Sounds pretty decent. Just let me know if the audio is too loud. Although I can try editing it, like copying out right now. Because I don't think the export audio. I have it at -20. What I could do is put it to -20, like -30. See if that changed anything. I'm gonna leave it at -25. If I have it here, like this far away, I'm just talking to myself. I wonder if you guys can still hear me. Maybe -20 instead, actually, just to make sure you guys still hear me. All right, yeah, I'm just testing audio. Okay, yeah. So audio check has been complete. -20 is pretty good. I'll try to let you guys hear about that. All right, cool. Let's hop straight in. So Spotify's not gonna be on today. Oh shoot, my thing's still on. Hold on, let me just fix this real quick. Why is it still on for this? Okay, cool. All right, we're gonna have to pull up a big ass stream. We're gonna put on a timer on screen. Do I have a timer? I put timer, but it should open clock still. We'll do a 2-hour, 30-minute timer locked in this real quick. And I'll leave it here because I don't want to see it all the time. So it's 6:42, then we're done that. Okay. All right, so we are going through. Hold on, I just want to have my speaker audio be way quieter. But it should say the same for you guys. It's just my headphone audio. Put at like 5. Okay. All right, so we're going over a bunch of stuff that I low-key. Hold on, looking at the weekly planner. I finished this on Thursday. This is moved. It says Friday, right, chat? Yeah. This is moved to Friday because I gotta. It's actually crazy. This is moved to today, and study stats is also moved to today. I have to start studying data science tomorrow, so we're gonna move this till today. So read data science chapter. This is gonna be on Saturday. Saturday's 11th. My first exam is the 18th, so I'm kind of cooked. That's going to be today. I got to finish stats 3 for the assignment, but we're going to compare some answers once we learn how to actually do this chat. So we're going to bust that out. Check if stream's working. Yeah, I can still see you guys. You can see me right there. So if anyone's chatting, we're chatting. Okay. Yeah. I'm going to just mute audio and have my phone open for chat. Audio is buns though. Hold on, let me just change the audio to. Cool. Yeah. All right, sweet. Let's hop in. Okay, so. Parameters, estimators, and sampling distribution. It's so loud still. I'll have it like 2. Okay. So what the heck is a parameter, estimator, sampling distribution? So we have the DGP, which is the underlying. I need water. Okay, you know what? I'll be right back. I'm gonna get water first, and then hop again. We have to grind all of stats today, and then we'll be back. All right, water has been acquired. Chatters. Okay. Realistically, I'm gonna have no one in chat, so. I'm gonna do that. Okay. So data generating process. So the DGP data generating process, the underlying process generates observed data. It consists of the population, complete set of data points, and the sample smaller area. So a parameter is a number summarizing a population. A parameter is a number summarizing a population attribute, right? So for the whole population, you know that parameter. A statistic, so parameters are, I'll say, we typically use samples to estimate population parameters. A statistic is a summary for a sample. A number that summarizes a variable based on the sample data. Right, so the sample mean is a statistic, and the population mean is a parameter. We know that, cool. But because samples vary, sampling variability exists between statistics from different samples. A sampling variability is basically the variation on the value of a statistic from sample to sample. So for example, if you had a sample mean, if you have, let's say you have 3 samples, right, of people, and you want to get their average height, their mean height. Out of those 3 samples, no one's going to be in the same sample, right? So then the heights are going to vary. So the mean height, the average height for those 3 samples is going to vary. Out of those 3 samples, the first one could have a different average, second average, third average for the different sample sizes. So if you take samples of the same size, then you take the sample mean. The sample variability is just how much each sample, I guess, varies from the true population mean, maybe. So parameters are constants where these vary with each sample. That makes sense. So the statistical inference draws conclusion about population characteristics or relationships among variables based on limited sample data. So you want to infer, basically, the population mean, population mode, population whatever, based off the data we get from our sample. But we also just said that depending on the sample you take, you can draw different conclusions. So how do we deal with that? Okay. This is where inference procedures, hypothesis tests, confidence. Okay, so that's what I was wondering for example. Okay, so hypothesis tests and confidence intervals are part of inference procedures. Okay. So we're gonna do, okay. So you use knowledge of sampling variability and or estimates of sampling error to help draw conclusions. What can influence these estimators? So we have sampling error, difference between statistic and parameter due to sampling. Okay. I'm just gonna react. So we have sampling error, which is the difference between the statistic and the parameter due to sampling, and also the bias, systematic favoring of certain outcomes or individuals during sampling. A good sampling reduces sampling error and probably has no bias, basically, I'm assuming as well. Naturally, larger samples reduce error, which makes sense because if the population has 10,000 people and your sample is half of it, well, that's way better estimate of your parameter than if you had only like 10 people in your sample. So our population, so we have a population and we have a parameter for that population, right? An unknown constant of that population. We want to estimate what that parameter is based off our sampling, or based off our samples. So a random variable as well for an estimator. So an estimator is a function of the random variable. And the sample is, hey, you know what? I can also get you guys to, hold on, if I put on, can I copy this? On desktop. 1280, right? That's super small. Okay, never mind. Sure. When I switch to this, how close is it? I'll have to check my phone. I want to make sure you guys don't fall asleep. I'm not gonna lie. Yeah, let me just check how that looks. Yeah, that's not too bad. Not too bad at all. Okay. Yeah, that should be it. Cool. Cool Z's. Okay. So, a proportion of gray hair. Estimator, the number of gray-haired individuals in the random sample divided by the sample size. Right, for proportion. In this case, because we're calculating proportion, that's how it is, right? Proportion of gray hair would just be basically how many people have gray hair divided by the number of people in that population. So that's what this would be. This would be, proportion of gray hair would be the number of people in the population with gray hair divided by the number of people in the population. So we're estimating that. Okay, so then what's the estimated proportion of gray hair? Well, if we take this random sample, a randomly selected sample of people, then we take all the number of the gray hair individuals, and then we divide it by that sample size to predict that for that sample. Then our estimate is the constant value we observe. So we get our estimator, which is our function. So technically this right here is the function, our estimator. Then what this evaluates to is our estimate, which is this value here. And it's that constant, the observed value of the estimator, right? So what this evaluates to is 0.25, for example. So then we could say that that's the estimate for this specific sample. Okay. So an estimator is unbiased if the expected value is equal to the true parameter, which is, I guess, hard to understand for me, but I think it just makes sense like in my head. An estimator is unbiased if its expected value. So basically, if the estimate is equal, but expected value and estimate aren't the same, apparently. I don't know how. I think it's saying here, if your estimator, if the value, like I'm saying, I don't know how you're shouldn't this be the estimate, but whatever. Because I guess your estimator, subtract your parameter, even though your estimator is a function. So I don't know how we're subtracting a value from a function. So whatever. It should be the estimate, but whatever. It should be your estimate subtract your parameter because they're both constants, so it's a number. That should be, if they're the same, that means there'd be 0. 0 squared is just 0. So then yeah. Estimated value of 0 is just 0. So I guess in this case, why it's a function is saying if you take your function and you have your results, if you subtract whatever the parameter is, the number, it should be the same thing as just calculating the variance in your estimator plus the bias in your estimator. But if your expected value of your estimator equals the parameter, then your bias is just 0. So it just equals the variance. And this is the mean squared error. Interesting. A lower mean squared error indicates that it is a better estimator. So low variance measures how much the estimator fluctuates across samples. Lower variance means more precise estimates. As the sample size increases, the estimator converges to the true parameter. The mean squared error. This is your error, right? The predicted value minus your actual value. And then you square that. And I don't know why we're getting the expected value of this, but sure. I might actually put this in the chat, I'm not gonna lie. Can I copy this? Copy image. We'll put this into chat real quick. Yeah. Golden hour thinker. Explained in great detail. Mean squared error measures how good an estimator is at estimating a true parameter. It captures the average squared distance between your estimator and the truth. The players, for example, an example. Parameter is blue, the true parameter. A fit. Oh no, that's just of this. Okay. The players. The true population mean. The estimator function of random sample data. X because the data is random. Thus, this is a random variable. The expectation is taking over all possible samples you could draw. The key result is that the mean squared error breaks apart into exactly two components: the variance of your estimator plus the bias of your estimator squared. Deriving it, start by adding and subtracting this inside the square. Expected parameter minus your actual parameter. Okay, see, that's your estimate. So that's basically your estimate, or whatever. Or not expected, your predicted. Your predicted, I guess, parameter minus that. Start by adding and subtracting this. Don't know why. Damn. Component 1 measures how much your estimator wiggles. This is purely about random fluctuation. High variance. Your estimates are all over the place depending on how you sample, how much sample you happen to get. Cannot be eliminated. Okay. Measures how far your estimator is systematically off from the truth. On average, this is a structural problem estimating yourself on random noise. Even with infinite data, your estimator converges to the wrong value. Okay. Low variance and low bias. High bias and low underfitting. Overfitting. Low bias, but high variance. That's the worst case. High variance, high bias. You're cooked. A sample mean is unbiased, but has variance of variance divided by the sample size of n. You could reduce variance by shrinking estimators towards 0, but this introduces bias. The goal is to minimize mean squared error, which means find the sweet spot between the two. Okay. Sure. So what is a random variable? It's a variable with numerical outcomes from a random phenomenon. For example, the number of days last week that a randomly chosen adult exercises for at least 1 hour. So in this case, the number of days is a random variable. Because the randomly chosen adult, we don't know who it is, right? It can be it's a randomly chosen adult. And because of that, because we don't know who the adult is, because we don't know who that adult is, because we don't know who that adult is since it's random, then number of days that randomly chosen adult exercise for is also going to be random. So that's a random variable. So the number of days could take on many, many values. And I guess, wouldn't the chosen adult also be a random? I mean, no, it can't be a random variable because the chosen adult isn't a numerical value, right? It has to be numerical. The amount of time that a teenager spent on social media on any randomly chosen day. The randomly chosen day, I guess you could say days or 1, 2, 3, 4, 5, 6, 7. But the amount of time is also a random variable because time is a number and also it's on a random day. We do have some conventions for naming random variables, uppercase for that, I know, and lowercase for the outcomes or the estimates, I guess in this case. Random variables can be described as expected value, which is the average value for x, and the variance of that random variable over the spread. So the average value for x. So the expected value of the estimator, I'm assuming what that means in this case is the expected value of an estimator. I'm just going to stand up real quick. My legs are kind of tired. The expected value of a estimator is it says there's the average value for x. So that means if you have a random variable, and let's say we have 10 samples, if we get the average, whatever, the average mode or whatever, so we get them, we have 10 samples, we calculate the mode for each sample, and then I guess we get the average of those modes, average of all those 10 modes. Is that going to be the expected value? I'm pretty sure that's what it means. I'm going to ask chat by just putting this in the chat. And just say automatic save is turned on. Yeah, okay. Okay. My intuition is telling me that, for example, the expected value of a random variable x, that, for example, is based on the average at the average value that x takes, the average value that x takes. For example, since the expected value of a random variable x based on the average is, based on the average, for example, my intuition is telling me that, for example, my intuition is telling me, the average takes, since the expected value of a random variable x is based on the average value that x takes, then can I say that, for example, if I have, I'm just going to say 10 samples of people and I get the mode of their heights, So the most repeated, I guess, repeated H-I-G-H-H-I or H. So the most repeated height, let's say, in feet. So anyone between, let's say, like 5'9" and 5'11". Oh, not 5 foot. 5'9" and 5'9.9". Right? Is that how it works? 0.9 of an inch, right? Because it's, or is it, because you're not, okay, if I'm 5'9.5", that's not 5'10", right? Yeah, I'm assuming this. So the most repeated height, let's say in feet. So anyone between 5 and 9 is considered 5'9". How does that make sense? It's considered 5.9. Yeah. So the most repeated heights. Okay. So so for example, if I have 10 samples of people, and I get the mode of their heights for each sample, then if I get the average of those 10 modes, then is that the expected value of X? And then that's where I get my picture back. Set higher. That's what I'm assuming it's saying here. Yes, that's what it's saying. So if you have an estimator, X, the mode of the sample, you're applying the 10 different samples, then you're averaging the result. The average of your 10 modes is the estimate, the expected value of your mode estimator. Why estimate of and not exactly equal? The true expected value would require averaging over infinitely many samples. With only 10, you only get an approximation. The more samples you average over, the closer you are to the true expected value. Okay. This is exactly where the earlier this becomes relevant, mean squared error stuff. Suppose the true population mode of height is 5'9", then if your average of those 10s also around 5'9", your mode estimator is approximately unbiased then. If your average keeps coming out as 5'8", no matter how many samples you take, your estimator has bias. One subtle point. This is called binning, /d, whatever, and actually can introduce bias on its own because you find it depends. Yeah. I know that. Okay, so basically that's what it means. Okay, so in that case, when we want to say what's the expected value, we can always get that now. So that's actually new knowledge acquired. The variance. Okay, I know this from data science that I've been working at. I have another class I got to study tomorrow, but okay, so for the variance, is it A? Yeah, variance var of X. Can I say that I know the formula, that it is equal to getting the sample mean for each sample. Because I know the variance is equivalent to S squared, which is equivalent to the standard deviation squared, of course. But standard deviation is just a square root of the variance. For variance, you take 1 over n minus 1, where n is the number of, like the length, the size of your sample, and you're going to multiply this by the sum. I'm using it in LaTeX. By the sum, where you have minus and this. So this is the subscript, which is going to be I equals, I guess, 1 all the way to n of so you want to get the sum I equals 1 to n, which is the size of your sample, and you want to get the squared, what is it called? The squared deviation. And the deviation is the actual value computed subtracted by your mean, which is going to be x bar. So bar x. And your subscript should be I here. So the actual value that we, not actual value, but the value in our sample. So for example, the way I see this is if you have 10 samples, let's just say 1, 2, 3, 4, 5, 6, 7, 6, 7, 8, 9, and 10, right? Well, obviously we can calculate x bar, which I'm just gonna say x bar. X bar is gonna equal the mean, right? That's gonna be the sample mean that we have here. So 1, 2, 3, 4, 5, 10. So then what's the S? This is 10 times 11 divided by 2. We know that formula. So 10 times 11 is 110 divided by 2. I actually want to say 55, but that could be right, could be wrong. I don't know. Okay, I'm right. Okay, 10 times 11, is that right? 110, yeah, okay. Making sure I'm not dumb. Okay, so that's 55. 10 plus 9 is 19. Plus 8 is 27. Plus 27, plus 7, I won't do the math in my head, 34. 34 plus 6 is 40, exactly. 40 plus 5 is 45, we know that. 45 plus 4, 49. 49 plus 3 is 52. 52 plus 2 is 54. 54 plus 1 is 55. So we know that's 55. So our mean is going to be 55. So what you do is you're going to take, oh, I forgot something. You take this, and you're going to square each one. So I'm going to add another bracket here, another bracket here, and you square each one. It's going to be like this, I think it's called the square deviation, or something like that. I know it was in data science class somewhere. So then you would take, for example, you would take 1 minus 55, and you take this number here, and you're going to square it. And you're going to copy this, paste 3, 4, 5, 6, 7, 8, 9, 10. And now you're going to go down to here, and you're going to have, this is 9, 8, 7, 6, 5, 4, 3, and 2, because that's all the numbers we have in our sample. And so once you do this, you're now able to calculate this part, and then you're going to add all these values together. So I'm just going to pretend it's like plus, right? And we have, oh wait, plus, what? Oh, okay. So you're going to add a plus. We'll just add these bars down here to pretend that we have this. And so whatever this value comes out to be, which I don't really want to do, I am doing that right? Yeah, that is our average. And then after you get all of these numbers, you're going to sum up all of these values together, and we'll call that value like sum, right? So we'll just say like t. Our answer is t. So after you take all these squared values, you're going to add them together, and you're going to get t. Then what you're going to do for t is you're going to take what we got at the beginning, the 1 over n minus 1. So 1 divided by n minus 1. We know that n is going to be 10 because our sample size is 1, 2, 3, 4, all the way to 10. So the size of this right here is 10. 3, 6, 9, yeah, 10. So then you take 1 minus 10 minus 1, or 1 over 10 minus 1, which is 1 over 9. So then you take 1 over 9, that's our value here, and we're going to multiply this by t, which should be our sums of all the squared deviations. So squared deviations, get the sums of that, divide it by 1 over n minus 1, and that should give us our variance. So I say, okay, so for the variance, can I say that it's equal to getting the sample mean for each sample? Sample mean for each sample, subtracting it from all values, and for each sample. Wait, so can I say that it is equal to getting the sample mean for each sample, subtracting each sample's sample mean from all the values in that sample, squaring. Okay, no, hold on. Let me just say, can I say it is equal to getting the sample mean? Because the variance, but will the variance be for all samples? No, right? Can I say that is equal to getting the sample mean? Because it's saying here, measures the spread. Okay, so for the variance, can I say it is equal to getting the variance for each sample, and then getting the average variance across, I want to say it's 1C, and then getting the average variance across all these samples. And I'm going to say like e.g. Get the sample mean for each sample. So e.g. I'm going to say for each sample, there we go. For each sample, get the sample mean. Subtract that sample mean from all values in that sample, squaring squaring that deviation, and summing up all the squared deviations, I guess, all the squared deviations, then dividing by 1 over the sample size minus 1. And this should be the S, right? Which is going to be our, no, not S, this is going to be our variance. We have to take the square root after to get our standard deviation. So this is going to be like this. I'm going to say example, right? I'm going to say equals t. I can just say s to the power of this. S to the power of 2 is equal to 1 over 9 over t. I want to see, do I get the, I didn't get the average yet, but I'm just going to say, is that right? I forgot to divide by 10. I'm looking at it, and I know I'm trolling. If you all just saw that, I'm trolling. I'm looking at it, and I'm like, I can't say it now because obviously I just saw the answer there. But my point is, I was looking at this 55, and I was like, usually the numbers at the end are greater than your average. How can you have an average greater than 10 or all of the? I'm like, what the heck? My issue here, I'm gonna just edit it real quick, is that your x bar is the sum of all that divided by 2, right? Or, 10 times 11 divided by 2. And then you have to divide it by 10. This should be 5.5. So let me just redo this real quick. I'm looking at it, I'm like, shouldn't 10 be smaller? So I'll just do that and say save. And just redo that answer. What you're describing versus, what you're describing is the sample variance, which estimates the variance of the underlying whatever. But this writes to the random variant measuring the true population variance. Okay. So the true variance of the population, a fixed unknown constant. Estimate, so S squared, which is estimate of variance computed from one sample. Average of this is the better estimate, which is what I'm trying to say, right? If you calculate the variance for each of the samples, kind of like how we calculated the mode for each sample, get the average mode, that's the expected value of X. If we get the average variance over all variances calculated from the samples, we should get a better estimate of the variance of X. The reason you divide by this, not n, is specifically so that when this equals this means is specifically so that the estimated value of this is equivalent to the variance of this. This means n is this is an unbiased estimator of this. Each individual won't exactly equal this, but on average, they will. So yes, averaging your variance values across 10 samples gives you an even better estimate of this, and it converges to the true variance. as you take more and more samples. So is that the same thing with here? Yeah, expected value of, okay. You square that, you get this. So if your entire population, then your true variance is this divided by n equals 10. The fact that that one sample S there won't equal the true variance, but average across multiple samples, it will converge to this. So why is our true variance 8.25? Oh, because you divided by 10. Whereas divided by n minus 1. But I mean, if I divided by 10, wouldn't it be the same? It's averaging this, but the deeper point is that even a single this with n is number is already unbiased estimator, which is the whole reason we use n minus n. So I can't use 1 over n when calculating the sample variance. I'm assuming the answer is yes. How much time have I been studying for? Only in about, what is that, 9 minutes? No, I did 2 hours and 30 minutes, I think. I don't know. When you compute this, are slightly smaller than your true deviation would be. This is because it's pulled, yes, slightly inflates the result. Okay, cool. So bias when you do this, unbiased. So yeah, just use n minus 1. Again, this is from data science. We didn't even learn this in stats yet. So I don't really know how, I'm trying to like mix these two classes together, and I'm confused because I don't see any way we get this. It literally just says, this girl's notes, and these notes are peak, right? But these notes are peak, but at the same time, it's like, I'm looking at them and I'm like, bro, how the heck are we supposed to get this by ourselves? Because there's no knowledge of explain. Like, what is this? It literally just said this. So how, if it said, okay, here's the information, calculate the variance of the random variable, how would I know what to do? There's literally no formula to calculate anything. Is she gonna be like, oh, what is this? The variance? Like, that's bullshit. Oh, whatever. Anyways. So now we're talking about probability distributions. A probability distribution describes values a random variable can take plus the associated possibilities. This can be represented via tables, graphs, or functions, and it must include all possible values and the probabilities sum up to 1, which makes sense. All probabilities, right, of a single like random variable, because it's a numerical value. For example, this is the number of days. So if x with a random variable is the number of days last week that a randomly selected adult exercised for at least 1 hour, then we can represent that as this table here. Because there's 7 days in a week, right? Sunday, Monday, Tuesday, Wednesday, Thursday, Friday, Saturday. So we can say 0 to 7, or you could say 1 to 6, or 1 to, I guess it'd be 1 to 8. So I guess 0 to 7 makes more sense. Wait, hold on. Sunday, Monday, Tuesday, Wednesday, Thursday, Friday, Saturday. 1, 2, 3, 4, 5, 6, 7. 0, 1, 2, 3, 4, 5, 6. Yeah, wait, hold on. This is 8 days. Wait. 1, 2, 3, 4, 5, 6, 7, 8. The number of days. Oh, it's not saying. Oh, okay. This is the. Okay, I'm trolling. This isn't the week. This is just saying the total, not day of the week. It's just the number of days that the person exercised. So either they exercise for no days. This is what this counts. So you can exercise for 1 day, or you can exercise for all 7 days in the week, and anything in between. But if you exercise for 0 days, it's also a chance, right? So that's why it's from 0 to 7. So it's like 1 to 8. Okay. So the probability that x is going to be 3, meaning the number of days this person randomly selected a blah, 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 equals 3 is going to be 0.32. It suggests that there is a 32% chance that a randomly selected adult exercised for 3 days last week. And again, that would be knowing this table, which is like the probability that the random variable equals this estimate, which is finally what I'm able to understand, is these probabilities right here. So this is the probability distribution. That's how the probabilities distributed among the possible values that x, the random variable x, could take, right? So it could take these random variables 0 to 7 of random numbers, and since those are possible values it could take, the probability is distributed across those possible values. So this is obviously, I think this is discrete. So in this case, all countable probabilities, so number of days. So yeah, so this is discrete. The reason why I said that is because this works for discrete measures, because we know, right? It has a countable list of all possible values. The number of days last week, it's either 0 to 7. You can't have 8 days, you can't have 25 days, you can't have 25.6 days. It's literally the full day. Either you trained for at least 1 hour that day, or you didn't, right? If you trained for 59 minutes, that day doesn't count. So it's how many days did you do that? Well, I did it for 4 days. There isn't 4.5 days. It's either you trained on that day for 1 hour or you didn't. So that's discrete because you can count all of them. So that's the reason why we use this notation. When we get to continuous, what we learned in data science and also here is you can't say this, because in the continuous one, you're trying to get the area under the curve. If you look at this distribution graph, what's it called? Distribution. No, it's called a density graph. So if you look at this density graph, density curve, whatever it says here, you can see that you're trying to get the area under the curve. If you know about calculus and integration, the actual specific value that x is equivalent to, like, let's say 0.4 is 0, because you're taking the distance. If you take y2 minus y1, if you were to take, I can't write, so I'm not going to save it, but if you were to take y2 minus y1 divided by x2 minus x1, you're getting the slope, which you learn in like linear relations for like a slope of a line, right? Excuse me. If you zoom really, really close to this one section, you're going to have something that looks like this. And you're going to have a line here and a line here. You're going to have your x1 and your x2. And so as you get closer and closer and closer to x1 minus x2 is going to equal 0, which we know is undefined in division. When you're dividing a value by 0, you know it's undefined. So if you say what's the exact value at, what's the probability that the nitrate concentration is going to be 0.4, what's the probability it's going to be exactly 0.4? The answer is going to be, well, 0, because there's no chance, there's no way it's going to be that. It's technically undefined, but it's like 0. So what you have to say is what's the probability that's less than or equal to that, which is going to be the probability that's less than it plus the probability at it. And since we know the probability at the value is 0, it's basically doing nothing. So technically, you're calculating the probability that nitrate concentration is less than 0.4 or greater than 0.4 or between 0.4 and 0.8. Like, that's how you would do that for continuous, which is exactly what this is going to go over. I'm just going to read it real quick to make sure I'm not yapping and saying absolute rambles. Okay. So, going back to this guy here. So we have this. Yeah, I know that. So could these any value within an interval? So for example, the amount of time chosen, day, example above. This is because time measured is a continuous variable, right? Time can be 0 because we said the number of days, but the amount of time spent is completely different, because the amount of time you could spend, 5, if you say the amount of like 5 hours, well, then you're confined to 5 hours, but the amount of time spent doing an activity could literally be 22 minutes, 14 seconds, 38 milliseconds, and 0.2 picoseconds, and whatever microseconds. So it can keep going forever, and you can just right, you can't really have 2 times the exact same unless you're like rounding, right? But then that becomes more of a biased estimator, bias, because now you're confining it, kind of like what the chat just said. So like, as you can see here, right, like the difference is between 2 hours and 1.9999 hours. You can keep going on forever, right? So technically it's continuous. The problem with continuous random variables is that unlike discrete variables, you cannot assign a probability to each individual value, right? Because they're infinite values. So if you were to do this, it would be literally an infinite probability of everything here. So you can't do that. So you have random variable y, the nitrate concentration of a randomly chosen sample of drinking water. A randomly chosen sample of drinking water is very, very important. I'll bold that real quick. A possible density curve, that's what I'm looking for. I didn't see that. Density curve can look something like this. So this is a density curve. This indicates that the variable can take any value in the specific area from 0 to 1 milligram per liter. The area under the curve is a specified range of values. What? In a specified range of values will be the probability for that value to occur, which is what I'm saying. So it's the area under the curve. So we could compute the area under the curve for this density curve between 0.6 and 0.8. How you would actually do that is you would get the probability of the nitrate concentration of a randomly chosen like bottle of water. The randomly chosen one, the probability that randomly chosen drinking water has a nitrate concentration less than 0.8. You're going to calculate that probability. Then you're going to take that value and you're going to subtract the probability that randomly chosen drinking water has a nitrate concentration less than 0.6. So you just take B, probability of this B, probability of like, how do I draw this, or how do I write it down? Yeah, sure. The probability that X is less than B, subtract by the probability that X is less than A. Where obviously A and then B, right? So B, as you're going to the right, your values increase, of course. So B subtract A. So in this case, it'd be the probability that X is less than 0.8 minus the probability that X is less than 0.6, looking at this graph. And so right now it says it comes out to be 0.42. And I think the reason why it comes out to be that is because the probability that X is less than this, you have to know a bit more information. But in this case, we just have like the software does for us. But like in this case, oh, actually you can see here, like it goes to 0.25 or whatever. Yeah. So the probability that it's less than 0.8 in what we learned in data science, once again, is probability of X. You subtract your mu, or your average, your population average, and then you divide by your standard deviation. So sigma, technically, right? I'll put this here. Put it in like this. And actually, I'll just use it in LaTeX. It'll probably be easier to do this in a LaTeX thing, so I'll probably do that in a second. Oh, I click save. I'm gonna cut this out, and I'm just gonna say LaTeX online, something like that. And we'll drag this here. I could do overleaf. What's Prism? It's a workspace. It said it looks pretty cool. AI LaTeX workspace. Start from scratch. Can I just create from scratch? Welcome to this. Can I just write, or do I have to use the AI specifically? I guess you might have to. I guess I'd say like LaTeX note book or something like that. I know overleaf, but I have to like do. There's only so many you can actually like keep. Okay. Well, I guess. CD. I don't actually know, because I could open anything. And it's going to open the previous one. Can I just open VS Code as like a new VS Code without a thing? I think I can. I'm just going to say new window. Exalt this. So yeah. So there's going to be no folder open for this, but it's fine. I'm just going to say new. And I can't save it though, can I? Control P. Can I just say like new.md? Can I not? How can I create one? It's gonna ask me to save it though. I can't like. All right, that's fine. All right. I don't really have any other LaTeX editors though. Okay. Terminal. We'll cd documents, and I guess I'll just make a directory right now. Just call it like LaTeX or something like that. cd LaTeX, and then make directory. I'll just say like stats, something like that. Stats 2244, cd stats 2244, and then I'm just gonna say code dot. But I could also ni. I could create one and just call it like explain dot markdown, and then exit this. So we have explain.markdown here, and I can paste this into this, and I can render this out like this. And then I can actually take this, boom, boom. I could add this, and then I could go to the front and add this. All right, so it gets rendered like this. So we have this mu, and we are going to subtract, or not subtract, less than. I don't know why I did that. That's weird. Oh, I'm using that. Oh, sorry. Less than. Same thing here. It should be less than. It could also be less than or equal, but like I said, it wouldn't really change nothing. Less than. What's it saying here? What? Oh, is it? Oh, is this from my spelling? Yeah, hold on. My fault. I have a extension, spelling extension that I downloaded for writing scripts here, so I'm gonna just disable that real quick. I forget what it's called. Oh my gosh, how many do I have? I disabled this, no? No, I want to know, I want to make sure it's already installed. Like, filter extensions installed, here we go. Spell right, here it is. I'll just disable from this right now. All right, cool. So yeah, we have this is going to be less than, and then you do the same thing to your value, to your number. So 0.8. 0.8. And you're going to subtract your mu value, and you're going to divide it by, same thing, sigma. And then we're going to just reload this. Okay. So you're going to have all of this done. I should have just Control V, right? Yeah. And so once you do something like this, you're going to have your sigma. So let's just pretend, I don't really know. I'm going to have to create one. I'm just going to say, let's say mu equals like 0.2 or something like that, with a standard deviation of sigma equals, let's just say 0.1, just to make it small right now. Then we could just test it like this. So we have mu and sigma. Probability of this minus this is the probability of this minus this. Oh, yeah. And then that equals the probability of this, obviously. And you want to subtract the probability of 0.6 instead of 0.8. And so what we're technically doing here is the probability that the x value is in between a, less than a, or greater than a technically, and less than b, which is what we're calculating. So the probability that x is between a and b, which is exactly what this density graph is technically telling us. What's the probability that's in between this right here? And so we have it looking like this. Probability of x is less than b, probability of x is less than a, and we subtract them. And what we're doing is basically this. This value I have in between is kind of useless, so I'll do this, like that. And so we subtract the probability that x is, yep, and yep. And so what we have looking at now is we have the probability, subtract by the probability, and we are going to be using phi when we use the z table. But this basically turns into z less than 0.8 minus 0.2, which is 0.6 divided by 0.1. 0.6 divided by 0.1 is 6. So let's just say 1. Okay, actually, I'll just say 2. 0.3. And so I'll change the standard deviation to 2. And then we would have z less than, and then we have 0.6 minus 0.2 is 0.4, divided by 2 is 0.2, right? 0.6 minus 0.2 is 0.4. 0.4 divided by 2 is just 0.2. So then we have 0.2. And then using our z tables, which we have here. Oh my, no, our normal table, z table, whatnot. We just calculate when it's z is less than 0.3. So probability of this minus probability of this. And we just have this as phi. And we have this as phi since they're both positive values. We have to just find phi at, did this? No. We have to just find phi at like 23. Wonder what happens if I do this. Does that change anything? No. Okay. Phi at like 2 or whatnot. Oh, sorry, phi at 0.3 minus phi at 0.2. Since they're both positive, and then we get this equaling 0.2. You can see that right here, which is 0.5793. And then that's 0.2. We need 0.3 first. My fault. So now we need 0.3, which is right under it. 6179. 6179, 5793. And then we just get this value. And then you can calculate this. I'm not trying to do that right now. Calculator, put that into here. And that's what that equals. So this is basically what that equals. And you can kind of, actually, I'll add a space anyway, it doesn't matter. So that's basically what that equals, yeah. So then you would say the probability is this, and then you would just say like, I don't know. Therefore, 3.86, I guess, 8.86 percent. That probability of, yeah. Therefore, probability this equals this. That's good. Therefore, probability that the random variable is between A and B. I guess A and B in this case. Yeah. I'll just say 0.6 and 0.8. By letting up here, we could just say A equals 0.6 and B equals 0.8. Now it takes into chat, and I can just say like, obviously it says 42%, so obviously I didn't get like I don't know the actual standard mean or standard deviation or whatnot. So if I put this into here, I can just check what chat's gonna say. Again, yeah, this also assumes that the standard deviation follows a normal distribution, and as we clearly see, it doesn't. And also the size has to be greater than or equal to 30 for the critical limit theorem to apply, which I don't think it does in this case, but I don't know. Yeah. So this just basically tells us 42%. Yeah, cool. So sampling distribution, a sampling distribution. So we talked about continuous random variables, so probability distributions, and there's the random variable it can take plus the associated possibilities for each one. Random variable has to be numerical and also has to be an outcome of a random phenomenon. Just some like stuff I gotta remember. So now that we're here, sampling distribution. So a sampling distribution is the probability distribution of all statistic across all possible samples of the same size. So the way I think about it is probability distribution was literally what we talked about up here. This is the probability distribution we have that a random variable can take given a discrete where's my OBS? Given a discrete whatever. Given a discrete random variable, right? Or the random variable is discrete. Here, we're just saying the sampling distribution isn't the probability distribution. The probability distribution isn't population distribution, it's probability distribution of a random sample. But the sampling distribution is the probability distribution of all of a statistic, so let's say the mean, across all possible samples of the same size. So that means, let's say, so it's basically how this, how the probability is distributed across each sample. That makes sense. The probability of the mean, for example, let's say as a sampling mean across all possible samples. So suppose we have a sample of 16 people from a population. Measuring their IQ score and computing the same mean, you get this. So we have a sample of 16 individuals. We measure their IQ score and we compute the sample mean. There are 3 possible outcomes from this scenario. How? How is there 3 possible? There's only 1 sample. Or maybe, oh, okay. So maybe it's, so technically it's a sample of 16, but they took 3 samples. Yeah, these 3 sample means. So suppose we are taking, I'm going to say 3 samples of 16 each. These samples each of 16 individuals from population. So 3 samples are in total. Because measuring their IQ score, competing. So there's 3 samples. Each sample has 16 individuals, 16 different. So no individuals in the same one. Is in 2, only in 1. Here are the 3 possible outcomes. So this is the 3 possible outcomes of their average or mean IQ. These 3 sample means are part of a larger distribution of possible sample means or sample values represented by the density curve. Yeah. So basically, this is the 3 samples. So let's say we took 10,000 samples of size 16. The sampling distribution would be whatever we're calculating. Let's say the statistic we're calculating, the average IQ, the mean, right? Mean IQ. We calculate that for each sample, each of the 10,000 samples. Then we take all of those values and we make a density curve like this. So let's pretend there's 10,000 samples taken. All of their mean IQ scores, we just graph them. We have someone at 0, or 80, 80, 81, 82, 83, 84.5, 88, so it's continuous, right? So it could be any value. But let's say we have right here, IQ of 90. If 300 of those 10,000 samples have an IQ exactly of 90, that's where this dot is right here. So it's saying that the density of it, density is obviously a formula to calculate it, but let's say there's 300. This is I don't want to say proportion, but it's the density of, right? I don't want to say it's the exact number, but it's not the exact number of samples that have a mean of 300, mean of 90. It's the density of it. So from, as you can see, I don't know how to explain the density. I guess I can search that up, but it's kind of it's more, okay, out of those 10,000 samples we took, there's more, more of the, there was, okay, out of the 10,000 samples that we took, there was more samples, or the majority of samples had an IQ at around 100. As you can see, it's right here. So 100 has the most, is shared value. So out of all 10,000 samples, you could say, for example, let's just pretend 50% of them got 50,000 out of all 10,000. 5,000 of them got an IQ, a mean IQ of 100, and so that's why that's the high one right there. And so not a lot of people, or not a lot of, out of all the 10,000 samples, not a lot of those samples had anything in between 80 and 90. So majority of them here. So we have a rule, which was the 66, 95, and 99.7% rule, which is from your sample mean, or like this mean value here of 100, from the sample mean of 100, one standard deviation away from both sides, of course, you have for one standard deviation away from the mean, you have 66% of your data is in between there. 2 standard deviations away, you have 95%. And then 3 standard deviations away, you have 99.7%. And so using the z-scores, which we know for 95, when you want to get the z-scores for 95, you actually calculate z of c, which is like c is like the critical value you want. And you go c plus 1 divided by 2. So let's just look at this. 0.95 plus 1 is 1.95. 1.95 divided by 2 is 0.975. And so you would go to here, and you would go to normal table, and 0.795, 0.795 should be somewhere here. Right here, 0.75. What did I say, 95? Hold on. Oh, I actually executed it there. 0.95, sorry, plus 1 is 1.95 divided by 2, 0.75. 0.75, if you look at it, is right here, which is 1.9, and it should go up to 6. So 1.96. So your critical value would be 1.96 because you're trying to get 95 or set of 90, not really the 95th percentile, but more of calculating that 95%, whatever. So anyways, I think that's what it's just telling us here. Looking at this graph, we can see that the sample mean values near 100 appear to be the most probable outcomes. What is important to recognize is that there are infinite sampling distributions. Here we are focusing on sampling distributions with a sample size of 16. We end up with a different distribution if we, let's say, use a sample size of 30, which means it probably look more like a normal distribution, which this one already kind of does. In addition, there would also be a different distribution if we had chosen a different statistic to focus on. So focus on something other than IQ, we could also have a different sampling distribution. Also, depending on the sampling strategy you use, you could also end up with different sample means, right? Because if you use if you use a bunch of different sampling strategies, you could end up with different data, of course. Meaning the characteristics of the sampling distribution of sample means based on a simple random sample would probably be different than the sample means if they had done a stratified sample. So the takeaway here is sampling distribution can vary on the sample size, the estimator, and also your sampling strategy. So this is what I got to kind of memorize. Whoops. So we have some symbols, meaning, and I don't really know how much I need to know about this, but I'm going to look at it as that's our parameter. That's mu, which is it's a parameter, which is the population mean for whatever you're looking at. Population mean, age, population mean, whatever. This is basically saying you're estimating the parameter of a random variable. We're estimating the parameter, yeah. Okay, so you're estimating the parameter of a random variable. We are stating that the estimated parameter is a function of x, where x is the random variable of sample data yet to be observed. So that the notation reinforces that the estimator is a random variable. The estimator is also a random variable, which is like, what? I guess, yeah. When we actually have our sample data, we apply the estimator to that sample data to get our estimate. We typically use a lowercase letter, so like lowercase x, to indicate the observed value of the random variable, which in this case would be x. So when we apply the estimator to our observed sample data, we get the estimate symbolized by the, So we're estimating. So when we apply the estimator to our observed sample data, we get the estimate symbolized by this. Notice the use of upper lowercase this. When we use letter x, it can be hard to distinguish between them, so we use another variable like y and lowercase y. As noted above, there are some parameters and estimators, and subsequently estimates that have traditional conventional means and as we can or symbols. So for mean, we have the parameter y bar x or y bar low bar estimate popular. Okay, so mu. Variance, we have sigma squared. S squared is your variance basically as well. It's really funny because variance is your standard deviation squared. Your standard deviation is sigma. So sigma squared is your variance. So basically the parameter variance, you use sigma squared. That's your variance of sorry, not parameter, your population variance would be like population variance of whatever, of height. That would be your parameter. And then your estimator, you would be, I want to estimate what the population variance is. That's when you use the hat on top of the sigma squared. And your estimate, you just use S squared, which makes sense because S squared is our sampling, like is a variance for that specific sample. And then standard deviation, exactly what I just said, is just take the square root of all this, which is just boom, sigma. So a random variable has numerical outcomes and also has to be from a random phenomenon, a random event. Expected value. So this expected value mean, what does it say here? Equals, so it equals the average of the random variable, but weighted by probabilities, not just averaging observed data. Not just averaging observed data, but weighted by probabilities. See, it just makes it more confusing. Measures spread, like how far values are from the mean. Again, we're saying all of this, but I don't see any questions or examples of how to calculate this. All I see is that it's there. If they ask me what is it, I can say what it is. But if they say, okay, calculate the expected value of, for example, the nitrate concentration example above, how would I do that? I have no idea. Estimator, a rule/formula, like sample mean this, to guess. Okay, cool. To guess a population parameter, right? True mean from data. It's a random variable, so the estimator is also a random variable because it depends on future data. So it's funny because the estimator is a function of a random variable, but that function is also a random variable, which I'm trying to think towards math. When you say f of x, x is, you don't know what x is, right? Theoretically. F of x is like a function that's of x. So when you say x squared plus 2, once you define x is 3, then it's 3 squared, which is 9 plus 2, which is 11. So then that value, you would say f of x equals 11 because x in this case is 3. So you would say f of 3 equals 11. So then are we saying that the function now is also a random variable somehow? Because I guess depending on what x is, it changes the value of the value of your estimator, which should be your estimate. Yeah. I just find it weird how there's two different notations. But sure. And then unbiased estimator is saying when the expected value of your estimator is equivalent to the parameter, you know it's unbiased, which means it's correct on average. And then your sample mean is an unbiased estimator for your population mean, or your true mean. Population mean, for the sample mean. So average of all data points in the entire population, which is hard to do. So average height of every adult in the country. The sample mean is the average of data points in your sample. So in a specific sample, in one sample of 16 individuals, the mean height, or let's say 100, The average height of 100 people, that's going to be your sample mean, because that's not the whole population. Key point is that the sample mean is a unbiased estimator of the true population mean. The larger your sample, the closer your sample mean gets to mu, which is the law of large numbers. Sample variance, by the way, measures how the spread of data points in your sample are around the sample mean. How spread it around sample mean. The key distinction boils down to what they measure. Your sample variance is the spread of the raw data points in your sample. The sample mean variance, the spread of the sample mean across repeated sampling. So I'm trying to get this down in my head, and it's making me absolutely go bonkers. But I think I'm getting close to it. Right. The sample variance. Think about, let's say we have a specific tape. Our population is everybody in Canada. That's a lot of people. I take a sample of 100 people, 100 people in Canada, by the way. If I compute the average height of those 100 people, that is my sample mean. My sample variance will be calculating how spread apart is the height of each person from that mean. For example, in a perfect society of whatever, someone has 1 meter tall, 2 meters tall, 3 meters tall. I mean, it's supposed to be feet, let's just say meters, right? And the last person is 100 meters tall. So exactly in the middle, 5.5 would be your sample mean. You're not 5.5, 50. No, 55, right? 100 times 101 divided by 2, 5,050. But don't forget that the 5,050 has to be divided by 100. So 50.5. Okay, cool. So we have exactly 50.5. That's going to be the sample mean. 100 people, I get all of their heights. The sample mean, assuming that everyone's like 1, 2, 3, 4, 5, 6, 7, 10, all the way to 100, the sample mean would be 50.5. So the average height of those 100 people is 50.5 meters. Now that's for this one sample. Now let's say I get another sample of a different set of 100 people, and I calculate their sample mean. And then I do that for another set of 100 different people. So these samples all consist of 100 people. If I take, let's say, 1 million total samples, which is crazy, but if I take 1 million samples and each sample has a size of 100 people, if I calculate each mean, that's the sample mean. Each of those, I'm calculating each sample mean. Now, if I take the sample mean variance, that's different. The sample, yeah, so I have that. So I have 1 million samples. Each sample has 100 people. Has 100 people. And I calculate the sample mean for each sample. Then I take that value, and if I take that value and I calculate the variance, the sample variance for each one. Let me just calculate the sample variance for each one. So then I take all of my million samples, and for each sample, I calculate the variance, which means in that specific sample, how spread is the data from that sample's sample mean. So each person in each of those 100 people, take all of their points, get the square deviation, subtracting it from the sample mean, adding it up, dividing by 1 over 100 minus 1, so 1 over 99. That's the sample variance for each specific. So each sample will have a different sample variance. The sample mean variance would be you take all of those 1 million samples, we calculate their sample means, then we take all of those sample means and we add up. So all of those sample means are not going to have their own value. So we're gonna have a million sample means. Now, if I take the average of those a million sample means, I now get a new sample, like a sample mean. That makes sense. Like a sample mean. If that makes sense. Sample mean. Like you get the sample means, and then you get out of a million samples, you get the sample mean, which is the middle. And I'm pretty sure you can take the variance of that by taking the sample mean of each guy, so getting the square deviation of that. And so that's going to be the sample mean variance. How much it values from that. So the spread of the running or spread of the sample mean. Yeah, so the spread is going to be across repeated sampling. And that's sigma squared, which is the variance, but it's of the sample. Variance. Sample mean. Okay, so that makes more sense. That took way too long. Okay, so now we have modeling. I have way too much to do, but I think I can do most of this. I'm gonna go eat though, and then I'll be right back. Eat some lunch, take a break, and I'll be right back, chatters. All right, we are back, chat. Okay, so modeling relationships. So we have to create a statistical model. A statistical model is a generalized description of how data are generated. This includes mathematical expressions, functions, tables, graphs, assumptions about data behavior or structure, and often use well-known distributions to represent patterns in data, i.e. normal distributions. Just checking that stream on. Okay. Oh, I didn't pause the timer, did I? Yikes. Okay, I don't know. Can I add time back? I wish you could like customize and like change it, but you can't. It is what it is. Who cares? Okay, so the goal is to fit a model to data. What? A goal is to fit a model to data that reflects underlying population level processes. So often use well-known distributions to represent patterns in data. So assumptions about data or whatever. Okay, so we have statistical models, which are generalized description of how data is generated. So we want to explain, okay, so this is our data. We want a general model to describe how that data was generated. So functions, you can use a table, you can use graphs, and there's some assumptions about the data's behavior or its structure. And so we often use some well-known distributions, normal distributions, t-distributions, whatever, to represent patterns in that data. And we want to make sure our model is a good fit for that data, kind of like a linear regression, mean squared error, coefficient of determination, all that stuff. Okay, so in a class of continuous probability distributions, normal distribution is a class of continuous probability distributions. Same with, am I trolling? Same with t distributions, right? Okay, so it is defined by a parameter, the mean and variance, or parameters, right? Which is this, the mean and the variance. Possible values are real numbers from negative infinity to positive infinity. It is bell-shaped, unimodal, and it's symmetric around the mean. Bell-shaped because it looks like, can't show the example, but bell-shaped, unimodal, which means it has one like mode, I guess, like one peak, because that's the number that appears the most out of all of them. And then, or that's not really mode, more of just one peak basically in the middle. So that's why it's bell-shaped. Symmetric around the mean because, it's bell-shaped, so it's symmetric. Okay, so if we had the symbol x, you're saying that this random variable, its distribution, or the random variable, follows a normal distribution. which means, yeah, sim x mu sigma squared. The random variable x, which I would have probably put like this, but I guess here you have to make it code, which is weird. The random variable, you make it code. Control E. Oh, I'm trolling. Control Shift E. All right. The random variable x follows, which is this, follows sim a normal distribution with a mean of and a variation of blank. Right. The random variable follows a normal distribution with the mean of mu and a standard mean of whatever, mean of mu, and a variance of your variance. So we have some models that we want to talk about. So we have our basic model structure and choosing between models. So like we said before, a model tries to explain how that data was generated. Since the real world is messy, we use models to describe some patterns. So grades tend to, for example, grades tend to cluster around 75%. So that's a pattern. You want to also be able to predict some future values. If you study for 10 hours, your grade will likely be whatever X value. Every model splits data into two parts. So every single model, it splits the data into two parts. The data is equivalent to whatever the model is plus the error. So the model is the part that we can explain, the mean, the trend line, all that stuff. But the error is the part that we can't explain, which is like that random variation. So suppose we are modeling some midterm grades Y. The simplest model is called the empty model, which is exactly what I used for my assignment, the empty model. So the basic model structure is that your data, you want to describe it. You want to describe how it was generated. So data is equivalent to model, which is the model, the part we can describe, plus the error, which is the part that we can't describe, the random variation. The simplest model is the empty model. We just say the average grade, or Y is the random variable that's saying we want to model midterm grades. So okay, Y is going to be the randomly selected. So any randomly selected person in the population, what will their midterm grade be? That's kind of what we're asking here. And so we're saying, well, we can have a model called the empty model and say, for any randomly selected person in our population, their midterm grade will equal the average population grade plus some error. And think about that for a second. If we have a population of 1 million people, we actually were able to get all 1 million people will take a test, and then they'll take the midterm, the specific midterm. We get their grades, and then we get the average. So let's say in this case, 75%. So the average grade across the entire 1 million people for this midterm is 75%. Any randomly selected person out of the 1 million people, their specific midterm grade, will be equivalent to that 75% plus some error. So maybe it'll be 80%, maybe 76%, maybe it's 20%, but that error is specific to that specific individual, which is how we get that. So epsilon, which I actually learned this is, if I click this, epsilon represents how far each student's grade is from the average, which is the error. Why is this considered an error? Well, we don't know such things. We don't know things such as why. Maybe they got higher than the average. Maybe they got lower. We don't know. We don't know that if they studied more, we don't know if they slept, it would change anything. We don't know. Since the model only uses the average grade, it ignores other factors such as sleep time, study time, etc., etc. So even if you suspect things like, oh, they studied more, but how much more, our model does not indicate that because it's just the empty model. So now we want to choose between models. Well, here are 3 models I think we have in this course. So consider some sample data of midterm grades that seem to show a bimodal relationship. So we might wonder why that bimodal relationship exists. We might propose several different models of what generated that data in the population. So the 3 different models we talk about in this course are the empty model. The bimodal grades are just random noise around a sample mean. No underlying reason. So you have just your sample mean in the middle, and your error can be anywhere. So that's what we have this. Where mu represents the average grade, and epsilon represents how far each student's grade is from the average. The pros, this is very simple, and the con, high error, it ignores the 2 peaks completely. Because we said here, I swear I just said, it says bimodal. So not unimodal, it's bimodal. So apparently, there's 2 peaks in this data, in this example. Using this, it ignores the 2 peaks completely. So there's going to be a lot of error. The categorical explanatory variable, which isn't a model, but whatever. So let's pretend you have a categorical explanatory variable. Not your response variable, but your explanatory variable. The one you think is doing the changing or whatever, and then the response variable is the one you see, the outcome that you examine or you see, you visualize or whatever. So let's pretend there are 2 peaks again, bimodal, and they exist because there are 2 distinct groups, students who studied and students who didn't study. So let's say the average of the people who studied is 85%, and the average for the people who didn't study is 65%, which is still crazy if you did study, I'm not gonna lie. There's a pro in that case. The pro of this model, which is we take the average of people who studied plus epsilon, and that equals y, and y equals the mu of people who didn't study plus epsilon as well. I don't know why it's just and, but sure. And so the pro explains the bimodality with a clear categorical variable, which is studied versus didn't study, or I guess you would say like, what would you categorize that on? Study versus didn't study. Like I guess you could say like status, maybe not status. Not really status. Study versus didn't study. Maybe like situation. Maybe you could say situation. The situation that they studied and the other ones that didn't study. I don't know, something like that. But the con is that it requires you to know who studied and who, and you might not know how. Yeah, you might not know how to study. So yeah, that's also the thing, right? You have to know who studied versus who didn't study. Separate them into the 2 distinct groups, and then once you do that, then you can get your data and everything like that. So that's one of the cons. The quantitative explanatory variable is saying that grades vary continuously with hours studied. So not 2 distinct groups. So in this case, instead of saying that there's 2 distinct groups that could determine your average, we just say, depending on how many hours you study, regardless of if you studied or not, just the hours, which is continuous, because like I said before, time is going to be a continuous measurement because you could have 1 hour, 1.2 hours, 1.1 hour, 20 minutes, 13 seconds, 14 milliseconds, like you keep going, right? So it's continuous. So in this case, that's why we're saying it varies continuously. So our study is what's going to be your explanatory variable, which is why it's quantitative and it's explanatory. And your response variable is basically not predicted, but like what any specific person any specific person's midterm grade is going to be. And so as we see here, we have B naught, which is like the baseline grade. So if you studied for 0 hours, this is canceled, and then you would just have 50%, for example. So 50% if you didn't study at all. The slope is obviously going to be this. It's a linear equation. And that's going to be, let's, for example, 5% increase in grade for every hour that you study. The pro is that it's more nuanced than categorical groups. And I want to make sure I'm using the word nuance in the correct... I was about to say dissertation, but I don't even know what that means. Nuance definition. So it's less nuanced, categorized by subtle shades of meaning or expression. Lowy's work has gradually grown more nuanced. It's gradually grown more categorized by subtle shades of meaning. Okay. So, okay. So it's saying it's more nuanced because there's more, I guess, like patterns, I guess. I want to make sure I'm learning this word properly. Categorized by subtle shades of meaning or expression. So it's more categorized by subtle shades of meaning and expression. A nuance is a very subtle, slight, or delicate difference in meaning, expression, or sound. Delicate difference. It refers to fine details that are not immediately obvious, but are important for a deeper understanding. So it's small, hidden, but it often involves shades of gray and complex situations, not just black and white. A nuance of meaning in a word, a nuance of expression on a face, or a nuance of flavor in food. So if something is more nuanced, that just means there's more slightly subtle. Okay, so it's like slightly subtle. Okay, slightly subtle pattern definitions or explanation that can be drawn from this model than from a categorical group model, categorical explanatory variable model. Okay. And the cons, again, yeah, it assumes a linear relationship because that's a linear equation. How do we know which is the best model? You compare errors is usually the best way. So calculate error for each model. So the actual grade versus the model's prediction. And then you square the average of those errors. Square and average those errors. Exactly, which is mean squared error, exactly what that means. But I'm pretty sure that's what you do. You take your actual grade values, you take what your model predicts, you subtract it, and this is basically how you create your epsilon, which is also equivalent to your what are they called? Starts with the E. Your R, your residuals. So you take your actual grade, you subtract your predicted grade, and then if your model predicts too high, your error is going to be negative. And if your model predicts too low, your error is going to be positive, right? If your actual grade is an 80 and the model predicts that you got a 70, which is too low, that means your error is going to be positive, which makes sense. And if you look back at it, right? For example, I'm trying to explain to myself. This is like a code part in the center. I don't know how that's done. I'm going to break out of it. Control Shift E for code. How do I put it in the center? Maybe it's like a certain type of block you can have. Maybe it's like a code block. Block equation. That's what this looks like. And this is a text. Turn into a block equation. Boom. Like that. Okay. So then you could say here, wait, what? How do I accept this? How do I don't know how to accept that. Begin cases. Interesting, I guess. Anyway, so what I was thinking is, so then, for example, if you had y, which we said, not y, well, I guess technically y equals mu plus epsilon, right? That's our empty model, right? So if our error is now epsilon, and we just say our error is calculated by our actual grade. So let's just say it's the x, and you subtract your model's prediction, bar of x. That's going to be the average, like mean or whatever. And that kind of makes sense, right? Because if mu, let's say mu is like 10, the average is 10, like the true population mean is 10, and your value that you got is 3, well, if your sample said, if your model was like, you know what? We predict that you got a 6. Well, then obviously, as you guys can see here, you would say y. I like how it doesn't do that. You have to go like this. And you would say y is equal to 10 plus -3, because your model was higher. The model predicted you to get a higher value, so that means your answer is negative. And then 10 plus -3, of course, y just equals 7. So then that's what this is saying here. And so this just works for any, okay. That makes sense. I'll delete that, I don't need it. But for here, squaring it, you take all your error, calculate the error for each model. The only question is, I'm going to ask chat, do we do this for every, like, for example, if we use the empty value, calculate the error, the actual grade versus the model's prediction. Let's take this. I'm going to ask chat real quick. I'm going to say here. So let's use the empty model as an example. We'll just say y equals, again, mu plus epsilon. Y equals mu plus epsilon. I'm going to say use some random data, use some random numbers to model an example, to explain. Okay, let's use the empty model as an example, and also the quantitative, right? Explanatory variable model, I guess. Y equals beta 0 plus, if I'm using my slight knowledge, beta 1 times hours studied. Which I'm pretty sure was just like X. Sure. Hours studied plus epsilon. Something like that. Let's go on. Use some random numbers to explain which, to show, I guess, to show how I can determine which model is better. Something like that. So let's use the empty model. Okay, so we just say we have same 10 students as this example I had up here somewhere. So we have same 10 students in this case. So let's say we have this data, same for both models. So we have 10 students. Hours studied is crazy, but yeah, their actual grade. So the 10th student studied for 10 hours, studied for 10 hours. The first student studied for 1 hour, blah, blah, blah. Cool. That's actually a good way to like just have in our head. So the actual grade went from a 55. And why it's a 55? Because remember, if they studied for 0 hours, it's a 50. So they just went plus 5%. I don't actually know how they knew it was plus 5%. I think they just arbitrarily did 55. Because I never said, if you think about it, the slope is quite literally, like for this function right here, it's literally 50. Oh, okay. It just went like, okay. Using least squared regression. We learned that in data science. So, okay, so we go here. we have their actual grades in the data. So apprentice is like our data, right? We have the hour study as a column, we have the student number ID, and the actual grade as its own column as well. Using the empty model, we can predict that the same value for everyone. There's 0 people, so I don't know. Yeah, I don't know. No passwords? Oh yeah. All right. I'll be back. I'm trying to learn stats. I'm getting generationally cooked. Well, not really, but I'm just trying to like understand it. Wow, this is hard. This is the one I have like high on. So I'm trying to just. No, yeah. Yeah, I told you I was standing up. I look outside and people were looking. And people were looking at me. I was like 100% doing it. It was good. Yeah, I was on the other side of the sidewalk though. I don't know. I was scared. It was like a All right, chatters, I'm back. I didn't put on the thing. I had to leave abruptly. But, I just had to check something. Yeah. Yeah. I don't want to move. Data. Alright. Alright, so we're locked. Okay. Rock. Okay. I did see when I was watching the back of my phone, the audio was a bit quiet. I'm not gonna lie. But now that I think about it, I put my headphones in, and I'm assuming that the audio already finished a long time ago. Okay. We'll go. This flow state. Make sure these are still Creative Commons, and we'll choose the next one. You're using matcha, right? I forgot a lot of. I don't know. W's. I'll slightly increase it here. We'll hope that that sounds good. Hold on, I need to check. Phones. I should probably post on Do Not Disturb though. Cause y'all don't need to see my chats. Okay. Whoops. Oh, you can enable. Bro, I already have the preview. Anyways, yeah. I'll lower this back to 20. I'll probably, whoops, put this down because it actually does lower the actual thing. I'll put this to 50. Why did it go to 51? Go to like 52 or something. There we go. All right, sweet. Yeah. There's these. Okay. Bow. Chat. Alright, cool. I didn't reset this though. We'll just reset that right now. Alright, back to this. Okie dokie. I actually some music though, so. Alright, I'll be back. Hold on. I got a body, I move at a blick. I got a homie to move at a split. Like Jip, you know it's a rip. Like Chop, like Roddy and Rich, I'm moving too quick. You know it's a split. Don't know, I'm moving like a hut. Don't know, I move like a jit. Alright, the empty model predicts the same value for everyone. Just the mean of what? What? Right. The mean of everyone. Oh. Just the mean of y. Wait, what? It predicts the same value for everyone. So, for example, mu equals your sample mean, which is all the means all the actual grades, right, divided by 10, which is 74.5. So every student gets a predicted grade of 74. Okay, so that's different. I was saying that it predicts the specific person's. Okay, that might be a bit different. Okay. So the empty model predicts the same value for everyone. Okay. Right, so you get 74.5. So every student gets a predicted grade of 74.5. And so you take the actual prediction, you subtract it, and you get negative this, and your error is just a squared value of this. You square all of this after you subtract, and that's like your it's kind of like your residual squared, technically. Then you do all of this, and the numbers that are actually close to your prediction have a smaller error, of course. And then when they're further away, like a 92 versus a 74.5, it's crazy. So the error is 206. So you have a lot of error. And so your mean squared error is the sum of all of your errors squared, right? And then you sum all your errors squared, like your squared errors together. You divide by 10 because there's 10 people. And so their mean squared error is 134.85. Using the least squares regression model on this data gives approximately, this is your beta value. So if you have 0 hours studied, you get a score of 50.1. And every 1 hour increase, you get your predicted score, your actual prediction score increases by 4.15. And so you can see, using that method, we get the actual values, and then we just calculate it based on hours studied, 1 hour studied, 2 hours, all the way to 10. So your predicted score is 91.2. All of this is here. Our error is just, again, taking actual, subtract your predicted, you square it to get your squared error, and then your mean squared error. Okay, so this was empty model. Okay. This is a regression model. Okay, I was like, what's empty? I see. And so you add up all of this, get the mean of it. So you add up all of this divided by 10, and you get 3.44. And so with our empty model, we have a mean squared error of 134, and with our regression model, we have a mean squared error of 3.44. You subtract it, and you divide it by the bigger one, and 97.4% reduction in error. 97.4% reduction in error. So the regression model is dramatically better because the empty model is ignorant. It predicts the same grade regardless of hours studied. The regression model uses the information that more hours studied is equivalent to higher grade, so its prediction is much closer to reality. The remaining small error, epsilon, is just natural randomness that no model can explain. This reduction in mean squared error by adding a variable is essentially what R2 measures, which is how much of the error the model explains away compared to the empty model. And R squared is your coefficient of determination. I'm just going to ask them to make sure. And R squared is your coefficient. I spelled that right. Fish. Of determination. Coefficient of your determination is the sum of your squared errors divided by the total sum of your sum of squared errors, total error from your empty model. In our example, that means that 97.4% of the variation in grades is explained by hours studied. Perfectly, zero error. And your coefficient of determination is your correlation for a scatter plot. So there's correlation squared, right? How much of y is determined? So explained by your x value. Coolsies. So we got some knowledge for this part. Now I want to go over to confidence intervals, and I think this stuff here is stuff I haven't done yet. So understanding confidence intervals, but I will be right back, Chen. I'm trolling. All right, we're back, chat. I was trolling. I'm gonna restart the project. I'm gonna restart this since we're already halfway. Okay, cool. All right. I've been streaming for 3 hours. I usually get 3 hour streams. Anyways, okay. So yeah, we went over that. Now we're going over this new thing called understanding confidence intervals. So you talked about a lot of chat. I'm not gonna lie. I've gotten a bit more understanding on some little things that they could probably ask here and there, but getting a lot of understanding is kind of crazy. I'm probably gonna go over the stats stuff, like the slides that we have posted as well. Maybe off stream because I'm not sure I'm allowed to stream that. I'm not gonna lie. And then that's pretty much it. bye.